I focus more on like computer engineering, which is a relatively new field. I feel like it's like a branch of electrical engineering. What it comes down to is basically computer architecture. I did research in like computer architecture, so um, what's interesting is like for a long time it's been like Moore's law was dominating. Dennard scaling, which says like
Moore's law is the one that's like technology gets like twice as fast every 6 months or something.
Number of transistors
Oh,
doubles every approximately 2 years, 18 months.
say that again. Say that again.
The number of transistors in a chip will double approximately every two
Yes.
years
What
for
is the
18 months.
significance of a transistor?
Transistor is like the fundamental building block, and they go down like atomic level now. So like we're at like 14 nanometer.
And that is like the basic block of computing.
Yeah, it's like a switch. It's like a
Like
on-off
a
switch basically.
0-1
And you make
thing?
common. Yeah,
Okay.
that's what binaries. The
Now,
representation.
can that law, can it not be changed and that whole process be accelerated
Well, that's
to
what's
rather
interesting. So
than,
that's where so
okay.
for like CPUs, right? Especially in like 2005 and stuff, you would notice every year you could get like a faster computer. That's because like the number of transistors would double, so the speed would double. Your power, like Dennard scaling says that your power will stay effectively the same when you scale transistors. That's dead now
Wait,
too.
wait, Dennard's scaling? Say that again?
Dennard
Solar?
scaling.
What is it?
It's you're calling me out here, man.
No, I don't know.
It's
That's
like
what I'm asking.
it basically has to do with like the power budget of a chip. Like you
Okay.
can keep the power the same, but get
More
out
out
of
of
the
it.
chip.
Gotcha.
Okay.
That's effectively
Remember,
dead.
I'm role playing the layperson because
Yeah.
otherwise I know everything about
Of course,
everything.
role playing. So we won't get too deep into like the transistor level. Let's go with the higher level perspective, like a CPU in general, right?
Okay.
It's a very general purpose. You can, that's why like your computer, your laptops, your desktops will have a CPU because it can do everything.
Right.
And they made single thread I guess application performance very very good in a CPU.
Right.
And GPUs came along, which are good at like again generalized compute, but more parallel like computations.
Okay.
Very arithmetic
Two
heavy,
things
like
at the same
parallel.
time
Yeah.
or whatever.
So that worked well for graphics, and people started using like crypto mining and all like AI workloads and stuff. But now we're at a point where like CPUs aren't getting much faster. Now we have like multiple cores, but
There's also, like, it doesn't demand as much, at least at the consumer level, right? But maybe at
so yeah, like you can make one processor for everyone, which
Right.
like when you say demand, did you mean like?
I think he means like, is this everything you're talking about and all the improvements? Mainly the enterprise customers are taking advantage of this, or
Yeah.
consumers are they?
Like they definitely made like data center CPUs and stuff. So what's interesting is the demand is now calling for just faster and faster compute, which like CPUs, GPUs. So there's a spectrum now. If we think about like this is one of the main important things of like computer architecture that I've learned is CPUs are okay. So if you have a graph of like power efficiency versus like programmability, right? And like just like performance versus like programmability and stuff. You have a CPU on one end of the spectrum, which is extremely programmable, but not very like energy efficient. You don't get high performance, especially like for certain workloads.
And programmable is like what a human can, how much advantage or value they can
Well, like
extract
fixed
out.
function versus like telling it to do something.
So what were
right?
the two things were programmability
and like energy efficiency or performance.
energy efficiency. How would that relate to in human terms?
Ooh, this is not something I've.
I thought I was talking.
So yeah, I just want to kind of share with you on the plane.
Okay.
You know how the flight is long. I was going from San Francisco to Istanbul, and it was a 14-hour flight.
So
and
this is a
I
good-
love those
yeah.
long flights because you end seeing so many movies. One of the movies which I had not anticipated was about Mary Shelley, the author of Frankenstein.
Oh.
And, I feel that she's the precursor of science fiction. And the reason I was asking you about the comparison with humans is, the whole creation, that Frankenstein creating a human or bringing a human back to life, or the artificial intelligence relates to, a machine versus a human being. That's kind of the context I'm asking you. Is how does this relate to my life? What's happening in your world?
Yeah, I'll break it down in terms of that then. So what we started off was like the technology aspect of it. So the computer architecture behind it. It's interesting because it's shifting, right? So now the workloads that are demanding compute power are like machine learning, AI. And okay, so to answer your question in a long-winded way, we have
Take your time. We got time, trust me.
Perfect. We have these algorithms that have been around since like the 60s and 70s, but compute is what's driving the advancements right now in like AI and machine learning. So we have all these algorithms that just couldn't be run effectively. We see these models that are being scaled like tenfold, 100-fold per year and getting way better results. And what are the results for? Like self-driving cars, language translation, things that help you. You would use AI in a way that you wouldn't expect right now. Like it's in everything, but when we think of AI, we think like, oh, robots that are like humanoid or like fully self-driving cars and stuff. There's like you can apply. It's basically just glorified statistics at this point, and we're trying to get to the point where it's like completely generalized knowledge. But what we had before, and my professor called it software 2.0, this way of like describing like having learning algorithms, right? Versus like algorithmically programming, functional based programming. Like everything is defined. We want to have like more generalized compute, but those are done with like neural nets and different kind of machine learning algorithms that are being developed right now, but they're run on the same hardware as the generalized computes, like the CPUs, the GPUs. And now we're seeing a shift in computer architecture where no longer are we just trying to make a general purpose CPU and scale it and get better power and speed out of it. We're seeing specialized architectures. So generalized versus specialized. You see like on that spectrum, you have CPU can do everything, but not super effectively, right? Versus if you want to you can have a fixed function ASIC, which is on the complete other end of the spectrum. It's really good at what it's designed to do, but you can't make it do anything else. And that's very expensive.
I'm going to ask you to stop here for a second, because maybe Michael can sense the humor of, me. My eyes are glazing over now because I'm a bit confused. And so could you simplify it even further for me and say,
I can.
In 2 years, you'll be able to do this, which you can't even anticipate, think about now.
Exactly, yeah. So now with this new hardware architecture where we can run compute more effectively, right? If you have something that would take days to run on a CPU, you can do it in hours on a more specialized processor, let's call it, or more specialized hardware. So I can buy
on Amazon with one click. Can I just think about something and we'll be able to buy it? Is that how my life will change?
That's one way. Yeah, sure. Self-driving cars is another way. The thing is, like, this is gonna, in my mind, it's gonna unleash like a whole new level of creativity to the world because everyone will have access to like machine learning. You won't need to know how to set up like a cloud instance or run like an FPGA or something to, you could just, and you won't need to necessarily know like the high level, like the machine learning algorithms or anything. When it's like deepfakes is something you can do right now. You can like, pull from GitHub, I think, this deepfakes repository and just train like a neural net to replace faces in a movie. Anyone right here could do with a little bit of setup and a powerful enough computer, I guess.
So we could all make our own movies, these dramatic Revenant style movies.
I mean, you could take like a scene and put Daniel's face in it, right? You could take Tom Hardy in his favorite movie and replace it with Daniel's face.
Rather than like putting it in.
I think it's
like it's automated CGI.
It's hard to.
I think it's relatable to like maybe like creating your own website, right? So when HTML first came out. Yeah, you had to know a lot to get a website up and running. You needed to know how to get the server up.
That's a really good analogy.
But now it's like the back-end stuff is being handled so that the layperson can just kind of sign in, put their name, and then a lot of that drag and drop stuff.
And the layperson can continue being a layperson.
Yes, exactly. And actually that's...
so the heavy lifting is done by others.
Yeah.
Like the hardware is thought of, the full stack connection from the end user of wanting to do something down to like making it effective, making it available to you is like a whole new. So that's what like the hardware is doing now. It's